This is the second lecture on lexical analyzer. I am sure that you must have gone through first lecture on lexical analyzer. So let us continue with the second part of lexical analyzer. When lexical analyzer scans source program for recognition of token, it may have to scan one character or more character beyond the token in order to recognize it. What I mean to say is, if this is my source program and in the source program a token is, for example, over here. Let's assume that there is a token over here. In order to recognize this as the token, lexical analyzer may have to look the next character or maybe more character in order to recognize that this is a token. Let's take example. If in the program I have equal symbol appearing, how do I know that this is a token? In order to know whether it is a token or not, I will have to look at the next character, because if the next character is equals space or some name of a variable, then in that case this is a token. On the other hand, if after the first equal sign there is one more equal sign, then this will not be the token, rather this will be the token. So in order to know that this is the token, I will have to look at the next character. So in this case, for the single equal sign, scanning by one extra character is required. So in most of the cases, in order to recognize the token, scanning by one character may be required. Let's take another example. I have, for example, not equal to. Now, in order to recognize this, no extra scanning is required. The moment I scan the equal symbol, I come to know that this is a token. Okay. But if I have equal sign, in order to recognize this as a token, I will have to look at the next character. Similarly, let's consider the identifier. If in the program I have an identifier, the lexeme is pos. In order to recognize this as identifier, I will have to look at the next character, whether it is white space, a punctuation symbol. Then only I can say that pos is a lexeme corresponding to the token identifier. Now, in all the example that we have taken, in all these examples, the scanning was by one character or no extra scanning beyond the token. In some cases, in some high-level languages, scanning by several character may be there. Now here is an example taken from the Fortran language. The first statement is do 5i is equal to 1.25, and the second statement is do 5i is equal to 1 comma 25. The first statement is an assignment statement where value 1.25 is being assigned to a variable and the name of the variable is do 5i. The second statement is a looping statement. It starts from the value 1 and goes up to 25. And what is the looping variable? The looping variable is I. Do is indicating that it is the looping statement, so it's the keyword. So the second statement is a looping statement and the first statement is a assignment statement. Now let us look at the lexemes and tokens in the second statement. In the second statement, what are the token? The token is, the first token is do, which is a keyword. The second one is number, and the second one is the number. Second one is the number, and the value of this is 5. The first one is the do, which is the keyword. The third one is an identifier, and corresponding to this, the location in the symbol table where the value information about I is there. followed by this next token is assignment operator. The next token is once again the number. The value of this is 1. Next token is comma, which is a punctuation symbol. Next token is once again the number, and corresponding to this the value is 25. So these are the tokens which are there in the second statement. Now let's look at the tokens which are there in the first statement. Tokens which are there in the first statement is the first token is identifier, and this is corresponding to the variable do5i, right? And the value of this is location in the symbol table where information about this is there, right? After this there is assignment operator, and then the next one is the number token, and the value of this is 1.25. So these are the tokens which are there in the second statement, and the tokens in the first statement is shown over here, right? Okay, when will I come to know that do is a token in the second statement? Until and unless I scan up to this point and see the comma, then only I scan up to this point and see the comma, then only I'll come to know that do is actually a token. So in order to recognize do as the token, I will have to scan up to this point. So scanning by several character is required in order to recognize do as a token. So the point is that when lexical analyzer recognizes a token and scans the source program, beyond the token it may have to scan one or no character in most of the cases, and in some cases depending upon the language, several character it may have to scan beyond the token in order to recognize the token. Let us now discuss a few examples. We'll take a programming statement and we'll identify tokens in them. First, programming statements, they are shown over here. If you examine this, you'll find that we have a macro call. We are defining a macro, and this is where we are giving call to the macro. And you know that macros are processed by the preprocessor. So before program is passed to the compiler, all the macros are substituted or they are expanded. So what we'll do is, before we identify tokens in this statement, we'll first of all expand the macro calls, and after that we'll identify the token. So when we expand the macro, the statement becomes b is equal to uh, b is equal to a multiplied by a plus c. So this statement after macro expansion, it becomes like this. So my program has got transformed to this. Now we'll identify tokens in this. So tokens will be, let's first identify lexemes, and then corresponding to each lexeme you can identify the token. So lexemes will be, the first lexeme is this, the second lexeme is this, the third lexeme is this, next one is this, next lexeme is this, next one is plus, and the last one is C. These are the lexemes which are there. And now you can easily identify token corresponding to each lexeme. For first, the lexeme is token is going to be identifier, that is the name of the token, and value will be location in the symbol table. The second token will be assignment operator. The next one is going to be identifier. The next one is multiplication operator, and followed by this another identifier, and then I have a plus operator, that will be the next token, and finally the last one is once again the identifier. So these will be the token corresponding to the statements that is shown over here. Let's now take another example. For the statement shown over here, we'll identify tokens. So first of all, we'll identify lexemes, and then for each lexeme we'll write the token. So the first lexeme in this statement is printf. Next lexeme is opening bracket. Next one is size of integer is %d. Next lexeme is comma. Next one is size of. Next lexeme is opening bracket. Followed by this I have int. Next lexeme is closing bracket, then I have closing bracket, and then I have semicolon. So these are the lexemes which are there in this statement. Now for each lexeme, let us write the token. Printf is a function in the C language. So for this, identifier will be returned as a token. So printf is the name of function which is defined in stdr.h. It is not a keyword of the C language. So this will be returned as an identifier to the syntax analyzer. Next lexeme is opening bracket. This will be written as it is. The next lexeme will be returned as literal. So this is the token name for this one. Now this the string which is shown over here, this string will not be parsed by the compiler. So that means the parsing of this will be done by the printf when the program is running. This string will not be parsed by the compiler. So do not confuse that this string will be broken size separately, off separately, integer separately, is separately, and so on. Do not confuse in this manner. So this will be returned as it is, will be returned as literal to the parser. Next token is a punctuation symbol which is comma. It will be returned as it is to the syntax analyzer. Next one is size of. What is size of? Size of, if you look at the specification of the C language, size of is an operator. It is not a function. Size of is an operator. So let's assume that this is returned as it is to the parser. Next token is opening bracket. This will be written as it is to the parser. Next one is int, which is a keyword. It will be written as it is to the parser. And then the closing bracket, which is that will be written as it is. Closing bracket once again written as it is. And semicolon, which is a punctuation symbol, it will be written as it is. So these are the lexemes and tokens corresponding to each lexeme for the given statement shown over here. In order to scan the program, Lexical Analyzer brings a program into a buffer. Let us assume that I have the single buffer and Lexical Analyzer brings a program into this buffer. Let's assume that the size of the program is large. So at one time, only a segment of the program can be brought into the buffer, and Lexical Analyzer starts scanning from the beginning of the buffer. When it reaches end of the buffer, then Lexical Analyzer will bring another segment of the source program into this buffer, overwriting the previous content that was there. If I have this scheme which is based upon single buffer, there could be some issues, and let us discuss those issues. If I consider the first scenario where a segment of the source program was brought into this buffer and Lexical Analyzer was scanning from this buffer, and now during scanning it has reached up to this point, and now it is looking for next lexeme, next token from this location. It starts scanning and it reaches end of the buffer, but it did not encounter end of the token. It did not encounter end of the lexeme. Now since it has reached end of the buffer, it will bring in the next segment from the source program into this buffer. So the previous content, so this content of the buffer will be overwritten. So there will be problem in the recognition of the token. And why is this problem arising? This problem is arising because a portion of the token is there in one segment and another portion of the token is there in another segment. So when I bring in the second segment, the previous segment is overwritten from the buffer. In the second scenario, let's assume that I have the whole token into the buffer. I told you that, and this is from where it is beginning, and this is where it is ending. I told you that in some cases you may have to scan several characters beyond the token in order to recognize it. So let's assume that if I want to recognize this as the token, I have to scan several characters beyond the token. So I scan several characters beyond the token, I reach the end of the buffer, then I bring in another segment from the source program, and once again the previous content will be overwritten. This token will be overwritten from the buffer. Right. So in both the scenario, in the first scenario, a portion of the token was there in one segment and another portion was there in the next segment. In the second scenario, though the full token is there in one segment, but the look ahead that is to be done in order to recognize the token, that is a portion of that is there in one segment and a portion of that is there in the second segment. So in this case, there will be difficulty in recognizing the token. And why is this is arising? This is arising because I have the single buffer. Uh, so that is why this problem is arising. Let's now talk about another scheme which is based upon buffer pairs. In this scheme, instead of using the single buffer, I am using a pair of buffer. And let me refer to them as buffer number 1 and as buffer number 2. How does this scheme work? I bring the first segment of the source program into the buffer number 1 and I scan from the buffer number 1. When I reach the end of the buffer number 1, then I start using the second buffer. I bring the next segment of the source program into the buffer number 2. I do the scanning from the buffer number 2. When I reach the end of the buffer number 2, then the next segment from the source program will be brought into the buffer number 1. Whatever was earlier there in the buffer number 1, that is overwritten. And then you do the scanning from the buffer number 1. And once you reach the end of the buffer number 1, you start using the buffer number 2, and this cycle goes on. So this is how the buffer pair scheme works. If this is a scheme that we have, what will happen to the problems or issues that we discussed in the previous slide? Let us talk about them. So let's consider the first scenario. This is my buffer number 1 and this is the buffer number 2. And I'm assuming that a lexical analyzer is doing the scanning from the buffer number 2, and it is in the process of identifying a lexeme which is there at the end of the buffer. When it reaches at the end of the buffer number 2, it did not encounter end of the lexeme, it did not encounter end of the token. So now it has to bring the next segment from the source program into the buffer. Where this will be brought? It will be brought into the buffer number 1. So now the portion of the lexeme which was residing in the next segment, that is brought into the buffer number 1, and scanning continues from the buffer number 1. In the previous case, what was happening was when I bringing the next segment, the whole buffer was overwritten. So even the first part of the lexeme, that was overwritten. Now that is not happening if I am using the buffer pair. So that problem is resolved. Let's consider the second scenario. In the second scenario, the lexeme was completely inside the buffer, but the look ahead that is required in order to recognize the token, a portion of that is there in one segment and the remaining portion is there in another segment. So when I'm scanning the look ahead and I reach the end of the buffer number 2, then the look ahead is not yet over. I have to bring the next segment of the source program where this will be brought. It will be brought into the buffer number 1, and after bringing it into the buffer number 1, I continue the scanning in the buffer number 1. But the token and the look ahead that was there earlier, that is there in the buffer number 2. So even the problem number 2 or the issue number 2 that we discussed, that is also resolved. So if I make use of the buffer pair, earlier issues and problem that we discussed, those issues and problems, they get resolved. In order to design the lexical analyzer, first thing that you do is design the token. How to design the token? We talked about this in the previous lecture, in the part 1 of the lecture on lexical analyzer. Having designed the token, the next thing that you have to do is specify the token or describe the token. So now we are looking at how to make a specification of the token. In order to specify the token, we make use of regular expression. So let's say if the token is comparison, in order to specify this, I make use of regular expression, and regular expression for comparison is this: less than, union it with, less than, equal to, and so on. So this is the regular expression for comparison token. So this is the specification of comparison token. In the similar way, whatever tokens that I've identified, for each of the token, a specification can be done using the regular expression. I can now assign names to regular expression, and then I can use these names in the subsequent regular expression, and this brings a lot of convenience while specifying the token. In this case, I call it regular definition. The example is shown over here. So if you consider this regular expression 0, union it with 1, union it with 2, and so on up to 9. Now this is a regular expression, and this is being assigned a name. The name which is assigned to this is digit. So this regular expression is being referred by the name digit. In the subsequent regular expression, I will refer to this name. Now here is another regular expression, most significant digit, MSDG, and this is representing the regular expression 1 union it with epsilon. So either 1 or epsilon. Then I'm writing a regular expression for marks that could be from 0 and up to 100. So most significant digit can be 1. After that, I can have 2 digits. Each one could be from 0 to 9. So this is the regular expression which is representing the marks out of 100. So when I assign name to the regular expression, I refer to that name in the subsequent regular expression. There is a lot of convenience in writing the specification of the token. So in such case, I call this to be the regular definition. Let's consider few more regular definitions. Let's consider the regular definition of identifier. Identifier begins from letter. After that, there can be any number of letter and digit. So I'm writing a regular definition for the letter, which is over here. Then this is the regular definition for the digit, and this is the regular definition for identifier. It begins from letter, and after that there can be any number of letter and digit. So this is the regular definition of identifiers. Let's now consider a regular definition of number. Before we discuss that, let us discuss different ways of writing the number. For example, 953. This is one way for writing the number. Another could be 55.893. Or I can write the number like this also, where I make use of exponential format. So for example 28 capital E plus 15. So here the number has been written using the exponential format. Regular definition should be such that it covers different ways of writing the number. So this regular definition is representing the single digit. This one is representing one or more digits. This one is representing optional fraction part. This fraction part 0.893 may be there or may not be there. For example, it is not there in this number, so this is optional. So this regular definition is representing the optional fraction part. This epsilon is making this optional, and this is decimal point followed by one or more digits. Exponent part is optional, may be there, may not be there. For example, it is not there in this number, it is not there in this number. So this epsilon is making it optional, and if it is there, then this begins with the letter capital E. After that, there is optional plus or minus sign, and there will be digits followed by that. Now this is the regular definition of the number. So it begins with one or more digits, followed by this there could be optional fraction part, and followed by this there could be optional exponent part. Which operator do we use in writing the regular expression? I use union operator, I use concatenation operator, I write one regular expression followed by another and they get concatenated. I use star operator, which is the closure operator. Now I'll consider few extensions of regular expression, and if I use these extensions, then writing a regular expression becomes easier. One extension is a plus operator. When I apply a plus operator to any regular expression, that means one or more instance of that. So r plus means that one or more instance of r. So r plus is equivalent to r star. Another operator is question mark operator, and this means 0 or 1 instance. So r question mark means 0 or 1 instance of r, or r question mark is equivalent to r vertical bar epsilon. The next extension is representing character classes. For example, in the square bracket, if I write 0, 1, 2, so it is the shorthand for this. Or in the square bracket, if I write 0-9, it is the shorthand for this. If I use these extensions of regular expression and apply them to the regular expression that we covered earlier in the lecture, they will become like this. The later will become like this. Here I am using the character class. Digit will become like this. Here also I am using the character class. In the specification of digits, I am using the plus operator. That means one or more instance of the digit. In the specification of number, I am using the question mark operator. That means 0 or 1 instance of this may be there, it is optional, may be there, may not be there. Question mark again, question mark again. So when I use these extensions of the regular expression becomes compact, and it becomes convenient to write or specify the token.